I'd like to project both f1 and f2 in Cartesian vector form. Let's start with f1. If we're interested in projecting f1 in terms of ijk or in terms of the Cartesian vector form, all we'd have to do is just project it onto the x-axis and find its x component. And we project it onto the y-axis and find its y component. And the x component of f1, isn't that just equal to 10 times sine of 21? Well, why sine? Because the x component is equivalent to this component. I know the hypotenuse, which is 10 newtons, and the component that I'm interested in is opposite of the angle, so therefore I use sine. And the y component, isn't that just equal to 10 times cosine of 21? Well, why cosine? Because that component is adjacent to the angle, so therefore I use cosine. If I were to express f1 in terms of ijk, I'd have to make sure that the x component of f1 is associated with the I hat, and the y component of f1 is associated with the j hat, and also that the z component of f1 is associated with the k hat. f1 is on the xy plane, so therefore the z component of f1 would just be equal to 0, meaning there is no z component. Well, let's fill in the blanks. f1x, it was 10 times sine of 21, I'll associate that with the I hat, plus 10 times cosine of 21, I'll associate that with the j hat, plus 0 k hat. I would like to take the two 10s out. So therefore f1 vector is equal to 10. That would be placed outside the parentheses. So I will have left would be sine of 21 I hat plus cosine 21 j hat plus 0 k hat. And of course that would be in newtons. Well, f1 is a vector, and a vector always has magnitude and it has direction. The direction of f1 on this diagram, I'd like to express that in terms of this dotted line. So the sense of direction of f1 is expressed in terms of the dotted line. Now the sense of direction of f1 is expressed in terms of ijk. It's expressed in terms of the Cartesian vector form, and this is what we call a unit vector. And just as the name implies, a unit vector, it has magnitude equal to 1. So the unit vector of f1's magnitude is equal to 1. Well, how do we check this? If we are interested in finding out what is the magnitude of this vector, don't we just take the length of that vector by taking the square root of sine of 21 squared plus cosine of 21 squared plus 0 squared? And indeed this is equal to 1. So the magnitude of a unit vector is always equal to 1, and its only purpose is to show direction. The direction of f1 on the diagram is indicated by the dotted line. That's the sense of direction of f1, and it is now expressed in terms of ijk in terms of the Cartesian vector form. So this is the unit vector of f1, and its notation would be the small letter e with a hat, indicating it's a unit vector. And more specifically, this is the unit vector of force f1. Well, that's not too bad. All we did was made sure that we are able to differentiate magnitude and sense of direction of vector f1. Well, let's try vector f2. Vector f2, the magnitude is 250. And its initial position is at 17, negative 19, and its final position is now at 5, negative 14. So therefore, if I am interested in finding the x distance as well as the y distance from initial to final, all I'd have to do is look at the two coordinates. Final minus initial is always true when you're looking for the distances from the initial point to the final point. So in the x direction, final minus initial, 5 minus 17, that would be negative 12. And final minus initial in the y direction would be just 5. This is a right triangle, so therefore if the two legs are known, 5 and 12, the hypotenuse would just be found by the Pythagorean theorem, which is equal to 13. Now I'm interested in the x component as well as the y component of vector f2. The x component, how do I find the x component? The x component, isn't that just equal to 250 times, I'd like to use ratio now, the x component, negative 12 is in the x direction, so therefore 250 times negative 12 over 13. 13 is the hypotenuse of the right triangle. And the y component, isn't the y component just equal to 250 times 250? The distance that is along the y is 5, so therefore it's 5 over 13. Well, just like f1, if we are interested in expressing f2 in Cartesian vector form, I'd better make sure that the x component of f2 is associated with I hat, and the y component of f2 is associated with the j hat, and the z component of f2 is associated with the k hat. f2 is on the xy plane, so therefore the z component of f2 would just be equal to 0. Let's fill in the blanks. f2x, that was 250 times negative 12/13. I'm going to have to associate that with the I hat, plus 250 times 5/13, and that is associated with the j hat, plus 0 k hat. I would like to take the two 250s out, and so therefore f2 vector is equal to 250, and all I will have left would be negative 12/13 I hat plus 5/13 j hat plus 0 k hat, and of course f2 is in pounds. And just like f1, f2 is a vector, and a vector has magnitude and it has direction. The direction of f2 on the diagram is indicated by this dotted line. That's the sense of direction of f2. That sense of direction is now expressed in terms of ijk, or in terms of the Cartesian vector form, and this is what we call a unit vector, and more specifically this is the unit vector of force f2. Well, the unit vector of force f2 has to have magnitude equal to 1. Can we prove that the magnitude of this unit vector is equal to 1? Why don't we just take the length of that vector? The length of that vector would just be the square root of negative 12 over 13 squared plus 5/13 squared plus 0 squared, and indeed that is equal to 1. The magnitude of the unit vector of f2 is equal to 1. The magnitude of f2 is not equal to 1. Please distinguish those two. The magnitude of the unit vector of f1 is equal to 1. The magnitude of f1 is not equal to 1. So please again distinguish those two concepts. I'd like to take a step further and define this angle as alpha. If I'm interested in finding what alpha is, I have the two legs of the right triangle. The hypotenuse is 13. So therefore, whether I use sine, cosine, or tangent definitions, it does not make any difference. Let's use the sine definition. According to the definition of sine, sine alpha, by definition, is opposite over hypotenuse. Opposite is 5. The hypotenuse is 13. So therefore alpha is just the arc sine of 5/13, and you plug this in your calculator. That comes out to be equal to 22.62 degrees. So therefore the x component of F2, it could be expressed in terms of this angle. Well, the x component is adjacent to alpha. The x component is adjacent to alpha. I know the hypotenuse, which is 250. So therefore the x component could be expressed in terms of the angle, which would be 250 times cosine of 22.62. And because it's to the left, I must put a negative sign in front of that term. How about the y component? Well, the y component is just equivalent to this component, and that component is opposite of alpha. So therefore I can express the y component as 250 times sine of 22.62. And so I'd like to now express F2 again in Cartesian vector form. F2 is a vector. A vector has magnitude, which is 250, and it has direction. The direction of F2, I'd like to express it in terms of the angle 22.62 degrees. So therefore the x component will be negative cosine of 22.62, and I'll have to associate that with the I hat. And then the y component of F2 would have to be multiplied by 250 multiplied by sine of 22.62, and I'll have to associate that with the j hat plus 0 k hat. And of course this is in pounds. So does that mean that negative 12/13 is numerically equal to negative cosine of 22.62? Yes, that's exactly what it means. Is 5/13 numerically equal to sine of 22.62? The answer is yes. We have expressed F2 in terms of Cartesian vector form, in terms of ratios, or in terms of the angle 22.62.